In this work, we propose a streamlined approach for humanoid locomotion using constrained reinforcement learning. We rely on the constraints as terminations method to enforce constraints in a minimalistic fashion through stochastic terminations during policy learning. In practice, constraint violations increase a probability of terminating the future rewards the agent could have achieved. This naturally guides the agent toward behaviors that satisfy constraints to maximize future rewards. We train policies using the proximal policy optimization algorithm and the massively parallel simulation of Isaac-Jim. Observations include standard proprioceptive measurements, the previous actions, velocity commands, and phases for the legs. We study 6 optional features that can be implemented as part of a reinforcement learning setup. These features are compared individually with respect to a baseline policy to assess how relevant they are for our use case of humanoid locomotion. Learning rate schedulers appear to be detrimental to performances compared to a constant learning rate. Clipping the norm of the global gradient and the loss of the value function has a slight beneficial effect. Applying push disturbances based on the result of Bernoulli trials has also a slight beneficial effect compared to pushing all agents at the same time. Providing privileged information to the critic or observations with no noise greatly improve performances. We hypothesize that these 2 features enable the critic to access learning signals with improved quality, which makes it easier to assess the value function to better guide the actor. We extend our learning scheme to humanoid loco-manipulation for transporting a package in simulation. Commands include information about the box and the target location, and the critic receives privileged information about the contact forces applied by the hands. To ease the pickup procedure, the robot starts with the package placed between its hands. The target location is placed randomly in a half circle behind the robot, with a radius of 1.5 meter. This behavior can be extended to longer distances by scaling down the goal distance in the observations to fall back to the training situation. The robot can handle push disturbances even when transporting the box. We can also achieve long-distance navigation, including turns during transport, by regularly modifying the goal position to guide the robot along a path. Note that all of these augmentations only use the policy that was trained for the 1.5 meter half circle. Finally, the robot can consistently transport smaller packages as well, here with a 15 cm box instead of the default 25 cm one. The robot struggles to properly release bigger packages at the goal location as it does not open the arms wide enough. Here, we focused on a minimalist task with limited domain randomization, but modifying the package size in future work could be a way to solve this issue.